So, ladies and gentlemen, let's continue with Chapter 1, Part 2, Molecular Transport of Momentum and Heat. So I'm sure that also here many of you are exactly knowing what I'm talking about. So on the left-hand side, we will have a look at a fluid. The fluid is in a gap between two plates, and at the time t equals 0, we have a no velocity because both plates are in rest, and we do not see any pressure gradient or something like that. We also see that both plates are have a distance with this denoted with a d, and if that is the case, then we do not see any velocity. That means the velocity is 0. So the velocity field u, depending on y, equals 0. That is what's the case at t is 0. On the right-hand side, we see more or less the same, but here it is a thermal problem. So on the right-hand side, we see a solid or maybe a fluid at rest between two plates or two other solids. Both of them have a certain temperature. The upper temperature, TO, is T, and the lower one is also T. So the temperature is the same at the time T equals 0, and therefore we do not see any difference in time, any difference in temperature, of course, and therefore we also see a uniform temperature profile, which is denoted by the temperature depending on y is just, it's just the given temperature T. Okay, so that is quite simple. But now what will happen if we have a look at another point of time? So again, here both schemes. And so on the right-hand side, again, t is greater than 0. So now take a look at this one. And now the upper plate starts to move from left to right. So that means that the upper plate has a certain velocity of capital U. So the velocity of the upper plate is 0 plus capital U. And then, of course, we see at very small times that, of course, the upper plate starts to move with the velocity capital U. And then that at early times, only fluid, which is very close to the plate, to the upper plate, so adjacent to the upper plate, moves with the velocity capital U. And yeah, of course. And then that maybe t equals 0 plus 1 delta t. And if we want to have a look at a point of time which is a little bit later, then of course we see more of the liquid or fluid moves with the velocity u0. That is due to the friction that the velocity, that the fluid adjacent to the plates exerts to the other fluid parts. So that means that, oh yeah, I have to write down, of course, this one is t equals 0 plus 2 times delta t, and so on. And okay, so that means that we see here a velocity profile that is not 0, but we see a velocity that depends not only on y, but also on t, so on the position y and the time t. More or less the same corresponds to the right-hand side for the temperature problem. So here, of course, we see a temperature plus a certain temperature, delta T, whatever. And then, of course, we see, for example, if this is not y and x, but y and t, then we would see something like, if this one here is delta t, we would see, of course, that at the upper plate, we have the solid next to the upper boundary with a raised temperature, delta t. And for small terms, we would see a very similar behavior compared to the behavior on the left-hand side for the fluid, so that only parts of the solid, which are very close to the upper plate, raise the temperature. And if we look at a later point of time, so that means blue would be 2 times delta T and red is only 1 delta T, then we see that the temperature will spread through the solid. Okay? I can't use it because that's a zoom bar. This one does not work. Okay. So, and so that means that here on the right-hand side, of course, we also have T greater than 0 and only solid next to the upper boundary raises its temperature. And on the left-hand side, only fluid next to upper plate raises its velocity. And also on the right-hand side, I just did not write it down, but I will do that. Then, of course, we will see a temperature profile T, which is depending on Y and T. Okay, so, and this one, of course, why do we see a behavior like this? This one, of course, is due to the molecular transport of heat or momentum. Due to molecular transport of heat and momentum. So that means that for the left-hand side, for the fluid, we do not see several currents from the upper boundary which move into the lower, which move towards the lower boundary. So the the momentum is only transported due to the microscopic or molecular velocity, to the molecular velocity of the molecules. Okay, so due to the Brownian motion, and this one transports step by step the momentum or the heat from the upper boundary towards the lower boundary in this case. Okay. So it's not due to convection, it's only due to molecular transport. Okay, so what will happen if we want to have a look at if the time went to infinity? Then, of course, we see here on the upper plate a velocity which is still capital U, and we see a linear behavior. So we see a steady state flow, and this type, so a linear velocity profile, is called the Couette flow. And here again, we see a velocity profile depending only on the position y and no longer on time t, and that is because it is transient. So here on the right-hand side, of course, it's very similar. We see here t plus delta t, and also here we will expect a linear temperature profile. So in both cases, linear profile. And on the left-hand side, we see the transport of momentum. On the right-hand side, the transport of heat. And from the left-hand side, we see that the transport of momentum is from regions with a great velocity to a region with a very small velocity. And that means, in this case, from top plate to bottom plate. On the right-hand side, for the transport of heat, we see the transport of heat from regions with a great temperature to regions with a small temperature, so the same direction. And that means that we see a heat flux from the top boundary to bottom boundary. If you want to have a look at the math stuff, then of course we see that we have a velocity vector which is with a definition of that it is proportional to the plate area times the linear behavior, which is just the maximum velocity divided by the plate distance. So that's the plate area, and the factor for this proportional stuff is the dynamic viscosity. And on the right-hand side, it's of course very similar. We see a heat flux Q dot, which is proportional again to the area of the plate times, and here again, the difference of the quantities, so delta t divided by the distance, so delta t divided by t, and the proportionality factor is the thermal conductivity, lambda. So this stuff is exactly the same, and we can also write it down as small q dot, which is the specific heat flux times the area. So I'm sure that many of you exactly know that stuff. So, okay. That means that on the left-hand side, we have, with this definition, a Newtonian fluid. And for that one, we have the definition that the shear stress tau yx equals minus the dynamic viscosity times the partial differentiation of u with respect to y, which is, in this case, as we have linear behavior, minus the dynamic viscosity times this linear stuff, u divided by d. So what exactly is tau yx? And if we have a look at our microscopic scale, then of course we have our microscopic infinitesimal control volume. And here, what is y, what is x? It's quite simple. The first one is the normal vector to the side we are looking at. So the y, of course, is x, y, z. So this one is the direction of the plate. And the second, the x, is the direction of the shear stress. So the shear stress is a tensor. And if we look at the subscripts, then we see that the first one gives us the area of this cube we are looking at, and the second one is the direction. So in this case, tau yx is exactly this part of the shear stress. Okay, so that's the Newtonian law for Newtonian liquids. And of course, for heat, we have something very similar, which is the so-called Fourier law. And this one is the specific flux of heat, Q dot, equals minus lambda times the partial differentiation of the temperature with respect to the normal direction. So in this case, it is y. And if it is linear, as it is in our case, we simply have minus lambda times delta T divided by dE. And of course, we can get the heat flux Q, just to get it back. We can just use the specific heat flux, and we have to integrate it across the complete area. And of course, we can also do that with the shear stresses. So if we integrate the shear stresses across the complete area, we get the force. So that means that here, in both cases, we have momentum and heat flux are both in the negative direction. So that means that both occur downhill, and we can also define the diffusivities. The diffusivities are at first for the transport of momentum, the kinematic viscosity, which is the nu, which is mu divided by the density, and the unit of nu is 1 square meter second. And the same, of course, we can do with the thermal diffusivity. And here we see that the kappa is the lambda, so the divided by rho Cp, and the unit of kappa is again 1 square meter a second. And of course, the same corresponds to molecular species transport. And this one, of course, is just called diffusion. And the diffusion coefficient, everybody should know, capital D, which also has the unit 1 square meter a second. And therefore, here you just see exactly why those quantities are called, or parameters are called, diffusivities. To compare it, of course, with the also very often used dynamic viscosity. We have that the unit is just 1 Pascal times a second, and that for lambda, the thermal conductivity, we just have 1 watt per meter and Kelvin. And if we see that we have that we are able to get the same units for all the molecular transport parameters for momentum, heat, and species transport, then of course we can simply produce a dimensionless number. So the ratio of diffusivities is a dimensionless number. And of course, all of you know that we can use dimensionless numbers in order to simply predict what will happen with the physics in our case, for example, with the Reynolds number, whether it is laminar or turbulent or whatever. Here we have the so-called Prandtl number, and Prandtl number is just the ratio of the diffusivities of momentum and heat, so nu divided by kappa. And so the physical interpretation is that it is the ratio of the molecular transport of momentum to heat.